Hi, welcome back to MEN 221. Today we are going to talk about how to solve frames and trusses and things like that by being a little bit smart about our strategy. So this is not about being methodical. This is the next step to it, being strategic, which means you should know how to solve it so that you can do things in a reasonably fast way, especially if you're doing things by hand. Okay, so let's go and talk about this. The best way to do this is go stop this video, go get a pen, paper, calculator, ruler and do it with me. You know, I've told you many times, you cannot build muscles by watching an exercise video. The best way for you to do is sit and do it, pause and complete the exercise along with me whenever you need, and then you will learn this much better. Okay, so did you pause? Did you get a pen, paper, ruler, everything? Okay, very good. Okay, let's start. So the basic idea is the following. It's not enough to just know the formula. You should know the meaning of the formula. So for example, when we talked about moments, so if you think about rotations around the x-axis, which is moments around the x-axis, they depend upon Fy and Fz. So remember, mx is yfz minus zfy. You remember this? So you can see that only Fy and Fz components will show up, Fx components will not show up, and it also depends upon the x and y values. Same way for moments around the y-axis and moments around the z-axis. They all require the other two forces. Not only that, the main thing is that it is not just the forces, they have to be off the axis. If they pass through the axis of rotation, they will not be able to turn it. They have to be away from the axis of rotation. So if your axis of rotation is like this, and your x force is like that, pushing like that, it will not be able to turn it. It will not be able to twist it. But if my F force is above or below, then it's able to twist. Right? Same way, if my Z force is this way or that way, it will be able to twist. But if my Z force passes through the axis, it won't twist. Got it? So that's the idea. We're going to exploit that. The whole idea is the following. By judiciously choosing the moment equations, you can actually solve as you go instead of keeping all the variables and getting lots of equations. This is only strategy. That is, if you don't know how to do it, what will happen is that you just get lots of equations. That's all. It's not like you won't know how to do the problem at all. It just means you'll get lots of equations for lots of unknowns, and you can solve it that way also. Okay, let's look at an example problem and then I will step you through this process. Okay, so we're going to look at a truss that represents an awning. You know what an awning is, right? So that's something that's outside windows or doors especially in shops, especially in Europe. So it's an awning, and you have a truss system. You can see there's a bar AB, there's another bar BD, there's a bar BC, there's a bar BC and a bar AD, and you can see all the dimensions. There's a 50-pound force acting on this side, and there's a 150-pound force acting down. What we need to find out is find all the reactions. Can you see the short link? That's a 2-force bar that connects the point B to the point C. So what's our strategy here? Basic idea is that it's better to draw many free body diagrams and extract only a little bit of information out of them rather than to draw one free body diagram and try to get everything. That's item number one. It's better to draw lots of free body diagrams and judge it. Second thing is, before you set up the equations, stare at the free body diagram and you will be able to figure out how many unknowns are there, and you can figure out some strategies. You cannot get more than 6 independent equations out of one rigid body in 3 dimensions. So if you have more than 6 variables, you will find that you will not be able to solve for all of them. That doesn't mean it's a waste. What it means is that you may be able to solve for some but not for all. Taking moments is always useful than taking forces. If it is a joint, like if I'm drawing a free body diagram for only a joint, then moment equilibrium will not help you. You have to do force equilibrium. So force equilibrium for joints, moments equilibrium is the first thing you want to do for rigid bodies. Got it? This is our high level strategy. Now let's look at the details. So first thing to do is, we are going to do moments first. I'm going to draw the free body diagram of the full truss. You should draw it yourself and see what you will get and see where the forces are. Can you see? At point A, it was a ball and socket. So I have 3 forces at point A. At point C, there are 3 forces at point C. And then at point B, there's only a short link or a 2 force member. So there's only a force there. All the others. Remember, the bar forces are inside the body. So you will not show up, it will not show up there at all. So when you draw this free body diagram, let's go back and I want to make sure our outline, the boundary for it is cutting that bar, cutting this joint and going like that. Can you see that? So what it means is that all the bars are completely inside. Both the ends of the bars are inside. So we don't have to worry about the bar forces. Okay. So very good. We got this free body diagram. Now comes the strategy. First thing is we count how many unknowns. There's 3 here. There's 3 more there. And there's 1 there. So there are 7 unknowns. So that means I will not be able to solve for all 7. Not the end of the world. It just means I will have to actually break up this truss one way or the other before I can solve for everything. Okay. Our idea is we are going to try moments. If I take my moments around the y-axis like this, first thing is it will only involve bx and by forces. And the nice thing is I am only worried about the off-axis forces. This one, those 2. These 3 forces are on the axis, so I don't care. These 3 forces are on the axis, I don't care. Only the off-axis forces will show up, and that too only by and bz forces will show up. So let's see. This is a bz, this is a z force. This is a y force, and you know the distances, so you can do this calculation very easily. You just have to do zfy minus yfz. If you do this, when I say if you do this, what I mean is it's time for you to stop and you do the calculation for this, and then you will be able to see what I got. And your signs may be different, but you will get the same number. Here it is. I got 150 pounds times the corresponding distance, which is 2 feet, and then bx times 3 feet. Notice the direction of my bx. It's like that. So I can solve for bx. The other thing, notice that I have units right there in the equation itself. So that it's very easy for me to see how the units gets cancelled out and what's the correct unit. So if you write down the units along with your numbers in your equation, you will see the units very easily. Okay, now, so if I took moments through the y-axis, I got this. Now, the next thing is take moments around the z-axis through A, that is this way. So if you take that, these are the 3 on-axis forces. Notice Cy is also an on-axis force because it goes right through A. Right? So the only things that are off-axis are this guy, that guy, this, and this. And since it's a z moment, only x and y forces will show up. And if you do that, you will get Cx. And I want you to do it and see that you got the number. Okay. What else could you do? Well, I've already taken z moment, I've already taken y moment. Let's take x moment. And then I'm going to take moments around this axis. If I take moments around this axis, all of these things are off-axis forces, but only some of them will show up, and it's pretty easy. I got Cz. So what you need to do to evaluate which things will show up is to be able to look at this formula and figure out which are the things which will matter. Okay. Once you know that, it's pretty easy to calculate, and all these x and y distances, x, y, z distances are from the pivot point. So the y distance for CZ is not 4 feet, it's 8 feet. That's why it's 8 here. Can you see that? So please pay attention to where you are measuring. Everything is through this pivot point. Excellent. So we got 3. Well, we use 3 force equations, 3 moment equations. You can do 3 other moment equations for a total of 6, or you can do forces. We are going to do forces. So here is the free body diagram of the full truss. Now, what are the things I already know? We knew 7 unknowns, but now from the previous calculation, we already got these 3. So we can try forces. So now I'm going to sum all the forces in the z direction, which is this way. And so that means I'll have this force, I'll have this one, I'll have this one. Right? I will get AZ plus CZ minus 150 equal to 0. I already know CZ is here, so take that, substitute it here, and you can solve for AZ. Excellent. You do the same thing. AX plus BX plus CX equal to 0, and then from that you can see BX is there, CX is there, so these two are there. So substitute, and then you can solve for this. Hey, what happens if I solve for try summation of forces in the y direction? I will get AY plus CY, AY plus CY minus 50 equal to 0. I cannot solve for anything. So we just move on. And come back with more info. This is our trick. Maybe I find out CY later and then I can do it. Okay, very good. So now let's see. Let's look at the joints. So I'm going to draw. This is my original figure. I'm going to draw the free body diagram of this joint. See how I am cutting the joint? When I cut the joint, these are the forces that we already know. This is our current list. All these forces we know. And here is my free body diagram for the joint. Can you see? All the joint forces are pointing away. And I have this 100-pound force. Where was that 100-pound force? It is this, BX. This is 50 pounds. So I don't know this, I don't know this, I don't know this. Since I cannot use moments, I will get only 3 equations. This is a joint equation. So I will get 3 equations, 3 unknowns. I can solve for all 3. So we are going to do that. So to solve for this, we need force vectors because these are all vectors pointing in funny direction. Force vectors is force times line vector divided by line length. You remember, this is unit vector. And now, if I want to find the component, I just look at the line vector component divided by line length. That's how I do the force vectors. Okay, so first thing I'm going to do is I'm going to sum all the forces in the x direction. So let's see. And I'm going to make this way positive. I'm deliberately choosing some funny direction to be positive because I want to show you that that doesn't matter as long as you are consistent. So if this way is positive, this is 100 pounds. These two don't have any component in the x direction because they are entirely in the YZ plane. This has an x component and this is going to be dependent upon this bar AD, the x component of this bar. So how much is that? That's 2 feet. That's what goes up here. Can you see this is 2 feet? And the length of the bar is root 8 feet. You can calculate that by doing some trigonometry and you will see that it will be root 8. Okay, so immediately you can get TBD is 141.4. Okay, now let's do the y and z forces exactly the same way. So here you go. Here's all the things that we already know. Here's our free body diagram for the joint B. Now, if I do FZ, let's see. If I do the z forces, this one won't show up, this one won't show up, and I'll get TAB, that guy, z component. Its z component is 3 feet. And then this length is 5, this length is 5. Can you see that? So because the 3, 4, 5 triangle, so if you calculate that, that's 3 and 5. So that's why I get 3 over 5, 3 over 5 negative. The other one is the x component, I mean the z component of this, which is minus 0.707, summing all this way positive. And so the other one, Fy, same way you do that. So this is nothing but just using force equilibrium. You can solve these 2 equations for 2 unknowns. It's pretty easy to see that I'll get TCB equal to TAB. Sorry, TAB is 114.59. TCB is minus 52.08. So minus, if I get, that means it's compression. That's why I put a C there. Excellent. We can go and we can now have a longer, so we now know all of these things. So you can see I'm gradually knowing more of them. So now I'm going to go to this joint and I'm going to draw a free body diagram of that. Before I do it, you do it, pause, do it and come back. Did you pause it? Did you do it? Look, watching me is not much help, okay? I mean, because even if I don't know, I can copy from somebody, but you'll have to do it in the exam. Know what I mean? So you better be able to do this, okay? So draw this free body diagram, try and figure out all the forces in this by yourself. Then look at what I have done. Did you do it by yourself? Did you get the numbers? Now look at what I have done. Here's my free body diagram. Did you get the same one? I hope you did. Okay, now let's do the same thing. Summation of all the forces in the x direction. Remember, x direction is this way. So this thing has an x component, and that's, if you calculate it, it's minus 0.707. And then TAD. This thing has an x component, this bar, and you know all the distances. So if you know the distance between these two things, you can compute that. And TBC is also the same thing. This equals 4.89. You can calculate that. That's the length of bar, length of AD, and this one is x component of AD. Excellent. So off you go. You do the same thing for y, and you can solve these two equations simultaneously because you know TBD from here. And you can solve these two equations, and you got two more bars. So you got this bar and this bar. We already know this bar. We already knew this bar. We already know that bar. All the bars are done. We have to finish up with the remaining joints. Next one. There's the last joint. Oops, sorry. There's the last joint. This is the joint C, and I'm going to sum all the forces in the y direction because I didn't know this. I can compute this from the C joint. All of these things are known already, and so it's a pretty easy thing to do. And then full system free body diagram. You go back. You remember we didn't know one of those forces. When we did the full system, we were not able to compute the CY and AY. Now remember, we computed CY from the previous one. Can you see that? From the previous one we computed CY, so I can go there and substitute it into the AY, and if I summation of all the forces in the y direction, and I will be able to get AY. Okay, so summary. First item, you should do moments first for the full free body diagram and see if you can solve for things. When you do moments, only the off axis terms will show up, the on axis terms will cancel out, and only the terms that are not in the particular moment will show up. If it is mx, fy and fz will show up. If it is my, fx and fz will show up, and so on. It is better to draw lots of free body diagrams to get little bits of information out of them rather than to draw one free body diagram and try to extract everything. Counting is important because you can see how much information you can extract. Out of a single ball joint, out of a single joint like this, you can get only 3 equations. So you can extract only 3 pieces of information. For a full free body diagram, you will get 6 equations, so you can extract 6 pieces of information. That's how the thing works. Okay, with that, we are done.